countdown, but now we are recording, so everything we say and do from here on is being recorded. So, any questions, issues, concerns, especially concerning calculus, but anything else will do too? Anything? All right. If not, that was your chance, folks. So here we are. Oh, okay, that's an expensive pen. I don't want to drop it. This is example 2. We're in chapter 5, integration. We're 5.3, Riemann sums and definite integrals on page 309, example 2, and we had gotten this far down in example 2. Just a little bit of review. Let's just go back and see. What was our delta x sub I? Well, I can't get it to move backwards. Okay, here we go. Delta x sub I was 3 over n. Your c sub I was then minus 2 plus 3i over n. We did that last time. Okay, minus 2 plus 3i over n, and your delta x sub I was 3 over n. All right. So here's a definite integral from -2 to 1 of 2x dx. That would be the limit as your norm. That's what that stands for. The largest interval on which you've broken it down, as that norm is approaching 0, the biggest one's approaching 0, so all of them are approaching 0, of this summation, I equal 1 to n of f of c sub I delta x sub I. Okay, so let's break that down a little further. That will be the limit as your norm is approaching 0 of the summation of, now the f, we forgot to do that one. Let's go back and get what the f function was. The f function was, wait, it was there on the page, wasn't it? 2x, that's it. Okay, so it's going to be 2, and because 2 is just a constant, I can bring that on the outside of everything. It doesn't even have to be outside of the summation. It can also be outside of the limit as well. Okay, that can come all the way out, and all we have is x left, and our x was x sub the c sub I. That's going to be our x, and remember that was -2 plus 3i over n. So that's the summation of -2 plus 3i over n. That's the f of c sub I. The 2 went on the outside, and all you have left is x. That is your x, c sub I, and your delta x sub I think was 3 over n, wasn't it? All right, let me just make sure I'm remembering. Right, 3 over n, -2 plus 3i. Okay, got it. Now, we can do a little more housekeeping with this, and let's do that. Bring out the 2, and then we'll have the limit as your norm is approaching 0 of, now, this, oh, I left this off. I equal 1 to n. Okay, n's a constant here. Okay, I is the variable, you might say, the thing that's changing in here. So anything that doesn't have an I in it can actually be brought to the outside. So what that means is, for the let's do it in steps then. I think I'll put it in a big bracket. The -2 is going to be on the outside, okay, times the summation, that's a pretty ugly summation sign, I equal 1 to n, this is this part, of just the number 1, okay? Okay, because we pulled the 2 on the outside. Plus, now, oh wait, we also have this 3 over n, which does not depend on I at all, so this is going to be actually -6. I forgot to write that. -6 over n. The -2 from here, the 3 over n from there. Okay, so -6 over n times the summation from 1 of I equal 1 to n of 1 plus, and then we have another 3 over n here, so I'm going to do a separate one for that. Now let's see, yeah, 3 over n here times the summation, wait, okay, sorry, yuck. We have this 3 over n and that 3 over n, so that's 9 over n squared. Yeah, get out of there. Okay, 9 over n squared. This 3 over n, that 3 over n come outside of that second summation sign, I equal 1 to n. Now, I hope you know what I'm doing here. I'm splitting this summation of a sum into the sum of 2 summations. Okay, lots of sums in there, aren't there? Okay, and then all we have here, if we have the summation, we pulled the 3 over n, this 3 over n out, all we have here is I left. Oh, here comes Jordan. Let me see if I can get him in. All right, and I do believe we have perfect attendance today again. Way to go, team. Okay, way to go. I'm pretty sure Esther has been moved to Cal 3. She should never have been in Cal 2 in the first place, but she told me what was happening. They wouldn't let her register for Cal 3. The system was screwed up. So she registered for Cal 2 because she'd do a drop and add the next week. Well, the next week came and they wouldn't let her do a drop and add. So finally I talked with the records office sometime last week, I believe it was late in the week, and said, look, what is going on here? And they said, oh, we've had this all over the place. This new banner system isn't picking up all the grades from the old system, and that's what it is. So they put her in the other class. I don't even know she knows about that yet, but I hope she does. But anyway, here we have, we finished that summation. All right, so take your time on this. It's 2 times the limit as your norm is going to 0. That's the largest increment, which means of course the n is going to infinity. All right, now this part here will be -6 over n. That's all outside the summation, but within the limit. Okay, now, and what's the summation of I equal 1 to n of 1? That's just 1 plus 1 plus 1 plus 1 plus 1 plus 1 up to n times, so that gives you n. Well, guess what? Those n's go out. Okay, plus, I'll put this in brackets again for now, and this one will be a 9 over n squared. That's outside the summation. And what's the summation? I equal 1 to n of I. Well, that's just, if you recall, n times n plus 1 over 2. Remember that? If you need to, flip back a couple pages to the first of the thing and you'll see that, oh no, this is back in 5.2. Back in 5.2, which is several pages back, page 295, the summation of, well, the first one, the summation of 1 from I to n is n. I pulled the minus 2 on the outside. And the second one, the summation of I from I equal 1 to n is n times n plus 1 over 2. All right, now we've got that done. If I can find my pen, there it is. Okay, now notice, sorry, notice here, these ends can go out. One end from here and one down here. Can't do anything with the rest of them yet, so let's proceed from here. So this will be 2 times the limit. Now at some point, oh, they started it back here. They started saying that the norm going to 0, and at some point here I've been saying it but I haven't been writing it. That's the same as n going into infinity. So let's go on and get that done. N going to infinity. Okay, that's where what makes the largest increment going to 0 is for your n to be going to infinity. They started that a while back. Wish I had. Okay, now this will be a minus 6, that's taken care of, plus 9 halves, we can take care of that, times, let's do 9 halves n, oh wait, I forgot the n down here, 9 halves n plus 9 halves, 9 over 2 n, this 2 and that n, times 1. The n goes with this one, the 1 goes with that one. Okay. Now, notice here, also the n's go out. There is no n to cancel this one out, so what do we have left? Minus 6 plus 9 halves. 9 halves is 4.5, so that would be what? Negative, okay, another way to look at it. Minus 6 would be minus 12 halves plus 9 halves would be minus 3 halves. You got a 2 out front here, so that's going to be minus 3, and then as n goes to infinity, this one goes to 0. So I get that summation to be negative 3. Now, that was a little sketchy, but hopefully you could follow the steps there. They're going to do it with their steps. Unfortunately, I can't erase my screen, so you're just going to have to read their steps over mine. Any questions before we go to that? Any step along the way here that I was losing you? I'm hoping you're stopping me when I lose you, but in case you didn't, anything now?
So what you did, you had multiplied 3 over n into the negative 2 plus 3i over n, right?
Okay. This 3 over n right here, is that right? Is that the one you're talking about? Okay. Yeah.
Yes.
I brought that outside the summation because it doesn't depend on I. The i's are being counted in the summation. This has no I in it, so I brought it on the outside. So when it combined with the minus 2 here, that gave us our minus 6 over n for the first term here. And then I did a separate summation for this one, and I brought out the 3 over n here, plus that 3 over n, well, times that 3 over n, that gave me 9 over n squared times the summation, and that just left me the I on the inside. Is that where you were meaning? Yeah. So actually the 3 over n came out here with the minus 2 and came out here with the other 3 over n, giving you 9 over n squared. Okay. Good question. Any others?
On the second step, how did you get negative 6 over n? And I got stuck right there.
Okay. Right up here, okay, it was 2, this all came down, 2 times the limit, blah, 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 blah. Now, in this one, what we had here was a summation I equal 1 to n of negative 2 times 3 over n. Well, the 3 over n has nothing to do with the i's here. Here's the only term that has an I in it. So everything in this first term, minus 2 times 3 over n, can come outside the summation. So that's minus 2 times 3 over n would be minus 6 over n. That's what came outside the summation. Not outside the limit, but outside the summation. And that left us for this first term, since we took the minus 2 out, the 3 over n out, all you had left was a 1. Okay? Now in the second term, I broke the summation here. If I could get my pen to show up. Where are you, pen? There we go. This summation I broke up into the first part, that's the minus 2, and then the second part was this one. In the second part, the summation of 3i over n times 3 over n. Again, the two 3's, 3 times 3 is 9, and the two n's, n times n is n squared. They came outside the summation, and all that was left in there was that little old I. So that's how we got that. This one came from the minus 2 times 3 over n. That came on the outside, leaving just a summation of 1. And over here, the 3 over n times 3 over n, which is 9 over n squared, came outside the summation, and that just left you an I inside there. Is that what you were asking?
Yes, sir.
All right. All right. Covered. Any others? Be sure to ask, folks.
I got one more question.
Okay.
So, on the last step, I see you had 2 plus 9n over 2 and then plus 9n over 2. How's the second one 9n?
Okay. Okay. What I did here was the n's went out and it just came to be a minus 3. Here we had 9n plus 9. You see that? I distributed, I skipped a step because I was running out of room. Okay, 9n plus 9 all over 2. Well, this 9n, okay, I had already taken out one of the n's here. That one right there and one of the n's down here. So that just left me 9n over 2 over n. So that's 9 over 2, and the n's went out. And then the second part was 9 times 1 over 2, and that's over n. So that'd be 9 over 2n. So this part here came from this term times this, okay, 9n over 2n, and the n's went out, and then the second part was 9 times 1 over 2n, and that's what you got, 9 over 2n here. Now here the n's went out, here there was no place for this n to go, so as n goes to infinity, 9 over 2 times an incredibly large number is going closer and closer and closer to 0. Anytime you have a denominator getting bigger and bigger and bigger and bigger and bigger without limit, that's going to 0. Okay, but you wound up with a minus 6 here and a plus 9 halves here. So what I did was just change this minus 6 to minus 12 halves plus 9 halves would be negative 3 halves, and then multiply that by 2 and you got negative 3. Don't, yeah. Okay, was that sufficiently vague? Okay, good questions. Any others? Okay, again, because I'm limited in floor space here, sometimes I skip too many steps. I apologize for that. Let's see how they do. They usually skip more than I do, but let's see what they did. They came up with the first thing, and they first changed the norm going to 0 to n going to infinity. Everything else stayed just the same here. Okay, now that maybe I needed to do that step, but it seemed like you could do that in combination with any of the steps. Okay, and then what they did, n going to infinity of this. Now what is your f sub c? From back at the previous, it was 2 times c, because the integral is 2 times x, so it's 2 times c. The f of c is 2x. So it's 2 times c sub I. The c sub I from the previous slide was minus 2 plus 3i over n. And then your delta x sub I, they left off the I here. Should have an I in there. That was 3 over n from the previous slide too. Okay? Now, see how they did it next. They pulled out this 2 times that 3 over n. That gave us 6 over n. Now they could have pulled the 6 all the way out. They didn't. They left it there. That's fine. Perfectly fine. They'll pull it out later. But you can't pull the n out here. They could have pulled the 6 out but left the n. Okay. Times the summation of minus 2, because this 2 went out, minus 2 plus 3i over n, and you see this whole thing went out. So this is what they got. I wish my writing was not in the way, but I can't change it. But if you hang on to that thought, we'll have a clean screen on the next one. So here's where it goes. The summation, the limit as n approaches infinity of 6 over n. Now this one they pulled the minus 2 on the outside just like I did. Let's go back here and see. Minus 2, summation of minus 2. Where is it? There it is. Summation of minus 2. They pulled the minus 2 on the outside and just had the summation of 1. And that's what we have here. And then on the second term, they did the summation of 3i over n. Now, why they kept that there, I don't know. Oh, they pulled the 3 over n on the outside and just left the summation of I. So here again, they pulled the 3 over n outside the summation, the second summation, and just had the I left inside. And that's pretty much what we got. Now, carrying this on a little further, seems like to me they should take that 6 on the outside, but I won't argue with it there yet. Okay, so that'll be the limit of this. I would do 6 times. Let me go on and do it. Okay, just doing the way they did it. That would then be 6 times the limit as n approaches infinity of, okay, 1 over n, and then this first summation here, is a, oops, I crowded myself too much. I'm going to put a minus 2 here. That minus 2 can come outside and go on top of the n. Now I don't want to separate it yet. We'll get to that later. Okay? And what do we have left? If the minus 2 is out here with the n, the 6 is out here, then the summation of 1 is just merely n. I didn't need bracket there, parentheses would have done. Okay, and at this point you can say the n's are going out. Okay, plus, okay, now remember I already took the 6 outside the limit, so you still have 1 over n here, and you have another n here, so this is a 3 over n squared, and then times this summation, which remember is n times n plus 1 over 2. Alright, and again, what I like to do is to get rid of this n so I don't have to carry them around any further. And then if you wanted to, and maybe I should have done this, this would be 3n plus 3. Distribute the 3 across there. Okay. Now, let's see how they did it so I won't mess up their right space. Okay. They left the 6 in there. So 6 over n, and this one just gives us 2n. Okay, that's fine. Minus 2n. That's this part. Okay. Plus 3 over n. That's this part. And there's that sum that we just did. I didn't close off my last bracket there. I should have, but I forgot to. Okay. Now, in this first term, okay, remember This is outside both of these. So this end can go into that end and that end. Okay? So then this will give us the limit. I don't know if I shouldn't write here because that'll mess up the rate. So that'll give us a minus 12 for this one. That can come outside. And then you'll have a, and like I said, I did this as 3n plus 3 here. Okay?
Why are you not taking away from the 3 over n?
Okay? I haven't gotten there yet. Yeah, okay. This n went into those two ends because these are all within the bracket here. So I factored out an n there and took out that one. Okay. Now this one is still there to deal with this one and that one. And that's what we'll see next. Here, I'll write it over here. This will be the limit as n approaches infinity. Okay, and what do we have left? We have 6 times a minus 2. That would be a minus 12. And here we have plus, okay, now I've already multiplied these together and got this. So that's going to be a 3n over 2n, because this 2 can multiply by that, plus 3 over 2n. Okay? This part of the numerator over 2n plus this part of the numerator over 2n. Okay. Now this is where those two go out, if that's what you're asking about. So that gives you the limit. You don't have to write this any longer. Okay, I'll go on down. They wrote it again. The limit as n approaches infinity of minus 12 plus, okay, doing all my mess here. Okay. All right. I forgot. I multiplied the 6 times this. I forgot to multiply it by here. When you multiply the 6 in here, the 2 will go in the 6 3 times, and that leaves you a 9. So sorry about this. This should be a 9 here and a 9 there. Sorry. I'm trying to do their way and mixing it up with my way. Okay. And you see here you have your minus 12 plus 9, because, oops, we lost those 2's, remember. Okay, sorry about that. And this, if you can read my writing now, this is your plus 9 from here, because the 2's went out here and the n's went out there. So that gave you just a 9 left over here. That's that. And here's your 9 over n, because this 2 went out when I divided it into 6. Okay, so this gives us a minus 3. That's from here. And as n goes to infinity, that goes to 0. So there's your answer, minus 3. And that's what they got. All right. So couple of different ways you can approach it. Be very careful on each step. I'm sorry I wasn't there at the end, because they were carried all the things inside and I had already taken mine on the outside. But anyway, you get the minus 3. All right. Any questions on that before we leave it? Okay. Because the definite integral in example 2 is negative, what does that mean? It does not represent an area of a region. Areas are never, by definition, negative, just like a length. Can you run a negative 3 feet? I don't think so. I mean, you could run backwards, but you're still running 3 feet, okay? Distances typically are considered an absolute value. Areas are an absolute value. Can you color in an area of negative 3 square inches? No, there is no area of negative 3. they are always positive. So this doesn't represent an area per se, but it does represent what you might call a net area. So definite integrals can be positive, negative, or zero because they don't have to be representing a net area. Okay? Well, they do represent a net area. They don't represent a total area. For a definite integral to be interpreted as an area, function f must be continuous and non-negative on the interval a to b. Okay? And that's what we hit before. Here we're going to hit it again. Now, if you look at this, this is the graph. This is 2x. That's the one we're doing from -2 to 1. So here we have a negative area here. Here we have a positive area here because this one's below the x-axis. That's above. When you add this one to that one, the 4 bars here will cancel out the 4 bars there, and that's why you have -3 as your answer. Okay? Negative because more of it's below the x-axis. So here's your theorem 5.5. The definite integral as an area of a region, if f is continuous, that has to be, non-negative, okay, on a closed interval a to b, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equal a and x equal b. Here's x equal a. Here's x equal b, vertical lines there. The function here and the x-axis down here. This area here is the integral from a to b of f of x dx. Okay, that's what we just did without any Riemann sums. It's just that. Okay, now as an example of theorem 5.5, consider the region bounded by f of x equal 4x minus x squared, the x-axis, and we're going, and that's it. That's all they tell us. Because f is continuous and non-negative only from 0 to 4, because this is the graph of f of x equal 4x minus x squared. That's all she wrote, folks. Yeah, the function keeps going down here, and it keeps going down here, but the area is between for the non-negative portion of that function. So that goes from 1 to 4. So that's one of the first things we will do if we're talking about the area under a curve, the non-negative part of a function. We'll have to find those zeros and then find out if this area here is what we're talking about, and that is. Okay? Because f is continuous and non-negative only on this interval from 0 to 4. Down here, it would be negative. Down here, it would be negative. So this is the only place where this function is non-negative. Then the area would be the integral from 0 to 4, 4x minus x squared dx. Okay, now, thank goodness they're not making us do a Riemann sum of that. We could. It'd just be tedious. We can evaluate a definite integral in two ways. You can use that limit definition, which I'm sure all of you want to keep doing, or, big or here, you can check to see whether the definite integral represents an area of a common geometric region. Boo hiss, they still have going to have us do antiderivatives yet, okay? Such as a rectangle, a triangle, or a semicircle. Because we know the area of a rectangle, we know the area of a triangle, we know the area of a semicircle. Okay? So, we can either do limit definition or see if it represents one of those common ones. Alright, so here is example 3. They're still not having us do what I'd like to do, but sketch the region corresponding to the definite integral, then evaluate each integral using a geometric formula. Okay, so when it says sketch, folks, this is going to be a sketch. Alright, here's the vertical axis, here's the horizontal axis. The line f of x equal 4, that's a constant. I wish I could find this is such a little, there it is. Okay, let's say 4's up here, 2's there, 1's there, 3's there. So here's 4 up here. The integral from 1 to 3, okay, if that's, yeah, get out of there. There's 1, 2, 3, that's all we need. 1 to 3. Well, it would be that would be it, isn't it? Here is a function, f of x equal 4. That would be the horizontal line. Ooh, that's supposed to be a horizontal line that goes across there, and we're evaluating it between 1 and 3. What's the area under there? 2 times 4 is 8. Okay? Does that make sense? This is a constant function, f of x equal 4. That's the horizontal line, y is equal to 4. F of x equal y. Okay? And you're evaluating it between 1 and 3. It's positive, non-negative in all that area. The width of this rectangle is 2. The height is 4. 2 times 4 is 8. Agreed or not? Okay, I hope by your silence you mean you agree. Okay, let's do the next one. I'll try to not to. Okay, I'll do it here. There's a y-axis. Here's the x-axis. Okay, x plus 2. This is y is equal to x plus 2. Or f of x equal x plus 2. Well, that has a y-intercept of 2, right? And a slope of 1. So that's going up, if that's 1, 2, 3. Here it's going up to 4. Here it's going up to 5. And here it's going up to 6. Okay, so that's going to be, there's the line, y is equal to x plus 2, y-intercept of 2, positive everywhere from 0 to 3. Woo, that's supposed to be a straight line. Nothing quite. Okay, that's a trapezoid. Now remember how we did the area of a trapezoid? The width is 3, and it's 1/2 the sum of the bases. Now the bases are here. This is 2 here, and this is 5 here. 2, 3, 4, 5. So that would be 2 plus 5 over, well, 2 plus 5, which is 7, times the width is 3. Now, I meant to put the 2 plus 5 over 2, but that's what the half is out there for. So this is 7 times 3 is 21 halves, which is, that's a perfectly good answer, 10.5. That would be the area of this one. Uh-oh, what's that one? Well, we're going from -2 to 2, and we're going up to 2. So 1, 2, 1, 2, there's -2, 1, 2 is +2. Okay, when x is equal to -2, this is -2 squared is 4, 4 minus 4 is 0. Square root of 0 is 0. When x is equal to 0, that would be the next one thing here. Square root of 4 is 2. So then you're up here. And when x is equal to +2, 2 squared is 4. 4 minus 4 is 0. You're a 0 down here. Now what is that? That is, and you could do one more in there, like a -1 or a +1, that would be the square root of 3. Well, that's going to be somewhere up here. What this gives you is a semicircle. Okay? Why is that? Do it this way. Look, y is equal to the square root of 4 minus x squared. Normally we say f of x, but I went on and said that y. Square both sides, and what you get, y squared is equal to 4 minus x squared. When you square the square root, you lose it, and this would then give you x squared plus y squared is equal to 4. Well, that would be a circle of radius 2. We only were dealing with the positive square root, not the negative square root. Was somebody else coming in, or I just hit something down there? No, we got all 4 people here, so we're fine. Thought maybe someone had to leave and come back. So there's a semicircle. Well, guess what? And the semicircle of radius 2. Okay, my phone's ringing, but I'm not going to answer it. It's downstairs. There's a radius 2. That's the radius of this semicircle. Well, what's the area of a semicircle? 1/2 pi r squared. Because the area of a whole circle is pi r squared. This is 1/2 of that. So that would be 1/2 pi times 2 squared is 4. 2 will go in the 4 twice. So that gives me an area of 2 pi. Does that make sense? Yay or nay? No Riemann sums, nothing. These were nice regular shapes. We already knew the area to. You don't have to do the calculus as long as the function is non-negative in that region, and we made sure it was. This one was non-negative everywhere. If I could get my pen to come back. Where is it now? Come on. Oh, there it is. This was non-negative everywhere because it was 4, positive 4. This was certainly non-negative between 0 and 3. Okay, it wouldn't go negative until you got over here to a -2, and past that you go negative. So that's perfectly fine. So the 1/2, the sum of the bases here times the width. Okay, and then this is a semicircle, 1/2 pi r squared, circle of radius 2. Let's see how the book did. The first showed that same figure we did. F of x equal 4. So that's the height. The width is 2. 2 times 4 is 8. Here we had a trapezoid. One base over here was 2. The other base over here was 5. 1/2 the sum of those two bases. In other words, the average of those two bases would be 7/2 times the width is 3, 21/2. So that was that one. And then this one, of course, is a semicircle. If I could get my pen to show up. And 1/2 the base times the 1/2 pi times the radius squared. Radius is 2. 1/2 of pi, that would be 2 pi. So the first is area of a rectangle, height 4, width 2, area is 8. Not a single bit of calculus involved with that one. Okay. Second one, the region is a trapezoid with altitude of 3. Yeah, if you turn it over, the altitude is 3, the parallel bases are 2 and 5. Take the average of the two bases, 2 plus 5 is 7 over 2. 7 halves times 3, 21/2. Yep, and that's what they got. Okay, they did it in any order you want to. They did 1/2 the base height times the sum of the bases. Of course, you have to do it sideways to get that height. And the third one, the area of a semicircle of radius 2. Formula for area of a semicircle is 1/2 the area of a circle, which is 1/2 pi r squared, and that would be 2 pi, just like what we got. Any questions on those before we move on? Making sense? So, if the fact that you're dealing with an area and it's an area you can calculate in your head or without using calculus, do it, okay? But if it's an area you can't do in your head or without using calculus, then use your Riemann sum or whatever comes next, which hopefully we will get to one of these days soon. All right, so definite integrals. The variable of integration in a definite integral is sometimes actually called a dummy variable. Even though it's the independent variable, it's still sort of a dummy because you integrate it out because your definite integral, you have those two limits there. because it can be replaced by any other variable without changing the value of the integral. For instance, the definite integrals, the integral from 0 to 3 of x plus 2 dx, we just did that one. Well, guess what? You could call that t plus 2 dt. All you're doing is changing the name of the variable, but you're integrating out the variable because, it didn't matter what you called that horizontal axis. X, t, stickman, whatever you said, that's going to have the same value. Okay? Seems sort of strange, but it's true. Now, that was example 2 on page 309. We did theorem 5 on bottom of 309, and we actually did example 3. Those are our 3 areas. Now we're moving to properties of definite integrals. All right. Are we finally going to get it so we can do that? Now, the definition of the definite integral of f on some interval a to b specifies that a has to be less than b. A's here, b's here. That's what we're doing, from a to b, left to right. Okay? Now, however, it's convenient to extend the definition to cover cases where, what if a was equal to b? Well, if you picture that, it's not much of an area. Okay, we'll get there. But what happens if a is over here and b is here? How are we going to do that? Geometrically, the next 2 definitions seem reasonable. They are. And for instance, it makes sense to define the area of a region of 0 width, which is what we have when a is equal to b, and finite height, as long as it's not going to infinity there, then we can't tell what's going on there. That if it's finite height but no width, 0 times 17 or 17 million is still 0. Okay, so that would be 0. So here's definition of 2 special definite integrals. If f is defined at x equal a, that has to happen, and you have an integral flowing from a to a, guess what? That width, that distance between that is 0. Okay, so f of x dx, no matter how big f of x is, the width of it is 0. So that's going to be 0. Now, if f is integrable on a to b, then what if you have the upper limit down here and the lower limit up there? Okay, well, what that means, and this may not be as obvious, but that is exactly the opposite of flip them back. Put the lower ones on bottom, the upper one on top, and that gives you minus the integral from a to b of f of x dx. This stays the same, just change the sign. Now, they may do a little bit with that. Let's just see. No, they don't. They just move right into example 4. So what would you say the integral of sine x dx is from pi to pi? Anybody? The sine function looks like this, but pi is right here, and you're going from pi to pi. How much area did you cover? 0. So this is a 0. Okay, how about this one? The integral from 3 to 0 of x plus 2. Well, the next step, why did I write that down? I don't know. That's equal to minus the integral from 0 to 3 of x plus 2 dx. Okay? Well, we already did that. Remember, we just did this one. That's that trapezoid, and that was 21/2. So when you reverse the order of integration, you negate it. So that becomes negative 21/2. Without having to do any calculus there, we had already done the first one, and that gave us 21/2. So this is the opposite of that. because the sine function is defined at x equal pi. Of course it is. It just happens to be 0 there, but that's okay. And the upper and lower limits are equal. You can write that to be 0 without evaluating the sign at all, or the antiderivative sign, or anything else. Anytime your upper and lower limits are the same and your function is integrable, defined at that value, the answer is 0, period. Okay? And on the second one, the integral from 3 to 0 of this is the same as that given in example 3b, except that your upper and lower limits are interchanged. So to move them back where you want them to be, negate the integral. So that gives you minus the integral of 0 to 3 x plus 2 dx. We know what that is. That was our trapezoid, 21 halves. Now we negate it. So, sort of, well, I don't know. Okay, we'll just leave those alone. That's just two rules. They're always true. Okay? Any questions on those? If you have a higher integral going from a higher number to a lower number, negate the integral and go from the lower number to the higher number. That's it. If you got an integral going from the same value to the same value, that's going to be 0. As long as that the integrand is defined at that value. All right. Now, here is another, hopefully somewhat, excuse me just a minute, my throat's getting dry. Hopefully this is another, yeah, that makes sense situation. In this figure, let me make sure I'm not skipping anything here. We just did example 4, and now we're doing the additive property. Yeah, we're at the right place. We're on page 311 if you're following in your book. In this figure, this one right here, okay, the larger region, this region here from A to B of this function f, can be divided, if you wanted to, at C. As long as C is somewhere between A and B, you can divide the region there and do the integral from A to C of f of x dx, and then add to that the integral from C to B, because this area here plus this area here is equal to the area, complete area in between. And you might ask yourself, why would you do that? Well, maybe there will be times when it would, but it's just showing you a principle of integration. That if you, I've got my cord stuck, okay, my headset line just keeps popping off my pocket because I move my arms too much. Okay. Let me see who's called. Oh man, this is the dean. I guess I've got to answer, so if you'll hold on. Sorry about this. I'm going to pause the recording. Remind me to turn it back on. You may not be able to see it, but just check with me. Okay. So, in this figure, blah, 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 we've already done that. Because the line segment has no area, of course, that's from C to C, it follows that the area of the larger region, that's the whole area here, is the sum of this area plus that area. I mean, it kind of just makes common sense. But I can remember one of my teachers in high school, common sense is not so common anymore, so I don't know if you find that to be the case. So here's the theorem, 5.6, additive interval property. If f is integrable, meaning it can be integrated over this region, on 3 closed intervals determined by a, b, and c, then the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Now they didn't say this. They kind of imply it, but they didn't say it. But guess what? It's still going to be true if it's not. But what their implication here is that, yeah, here we go. The a is less than C is less than B. That's what they sort of assume, but guess what? This is true even if that's not. If C is over here to the right somewhere, you do the integral from A to C, and then do the integral from C to B. That's going to be a negative integral. You're still going to wind up with the integral from A to B. So it's okay even if C is outside of that, either less than A or greater than B, it still works. Okay? Now, here is example 5. Now, this is an absolute value function. Does anyone recall how the absolute value function looks? This is not a very pretty drawing, but if on the right hand side, when x is positive, absolute value of x is just x. So that's your identity. Get out of there. That's your identity function. Well, when x is negative, it's the opposite of that. So then it comes up like this. Yeah, these are supposed to be the same angles here. They obviously are not. And if this is going from -1 to +1, then your area would be this area plus that area. Okay? Now, F is continuous there, but it's not smooth. So this forms a triangle, that forms a triangle. Even though my drawing doesn't look like it, those triangles are exactly the same height. So you could split that in the area from -1 to 0 plus the area from 0 to 1. This is a triangle of area 1/2, because if you did the whole thing here, 1 by 1 would be 1. That's half of that, so 1/2 the base times the height. 1/2 of 1 times 1 is 1/2 plus 1/2, and that equals 1. Okay? This just says, because this absolute value function is defined to be negative x for any x is less than 0, positive x for any x is greater than 0, split that into the integral from -1 to 0. That's part of that of negative x dx, and the other part would then be 0 to 1 of x dx. And we can do both of those because they're simple triangles. 1/2 plus 1/2 is 1. They didn't draw a picture. They didn't do it. Maybe they will. Let's just see. That's equal to 1. Oh, they didn't. They didn't in the book either. So maybe what I did was helpful. I don't know. Here's theorem 5.7. More properties of definite integrals. Here's one. What if you have two functions, f and g? Both of these functions are integrable on this same integral from a to b. And k is a constant. Doesn't matter what it is, positive, negative, fraction, decimal, rational, irrational, it doesn't matter, just a constant. Then the functions kf and f, either f plus g or f minus g, either one, both of these are integrable. If f and g are both integrable, k is a constant, then kf is integrable and f plus g is integrable, f minus g is integrable on that same interval. Here's what the answers are. The integral from a to b of k f of x dx, because this is just a constant. Remember how those constants came outside the summations? They came outside the limits. That constant can come outside the integral, and sure enough it does. K times the integral from a to b of f of x, and we know that's integrable because they told us it was. Okay, so therefore this is. The answer is just going to be k times whatever the answer of the inside would be. Also, the integral from a to b of f plus g of x or f of x minus g of x, doesn't matter, is the integral from a to b of f of x, which we know that is integrable, and then you put the signs the same way, plus or minus the integral of g of x dx, and we know that's integrable because they told us it was from a to b. So you just take integral of f, whatever that is, either add that to the integral of g or subtract it. Now, here's one way of expressing that. The integral of a sum or a difference is either the sum or the difference of their integrals. As long as they're both integrable, that's true. Note that this property can be extended to cover any finite number of functions. That could be a f plus or minus g plus or minus h plus or minus k plus or minus m plus or minus n. Doesn't matter how many you have there, just use the integral of f of x plus or minus the integral of g of x plus or minus, on and on and on. That can be extended. Okay, now what does that allow us to do? Well, let's see if we can do this. They've already started the problem for us. Well, no, they haven't. Here is the problem. The integral from 1 to 3 of minus x squared plus 4x minus 3 dx. Okay, well, guess what? This is an integrable function. Whether you know it or not, it is. There's an integrable function. There's an integrable function. Now, they tell you what the integral of this first one is. Of x squared is 26/3. We don't know anything else, but we know that. We know the integral of the second function, x, not the all function, just the x. Integral of x is 4. And they tell us the integral of 1, from 1 to 3 is 2. Okay? Now, what we're going to do is take this one and use those 2, 3, 4 principles we just talked about and deal with them. So I'm going to write this down again. This time I will write it down. The integral from 1 to 3 of minus x squared plus 4x minus 3 dx. Okay. Here's how I'm going to write it. Okay. I'm going to split this into 3 integrals. That one, and that one. Just like we did with our sum and difference formulas that we just did. Now that first one, I'm going to pull that minus sign, that's a minus 1, outside the integral. So that'll be minus the integral from 1 to 3 of x squared. Agreed or not? Does that look like it's legal? Everybody okay with it? I don't hear any objections, so I'll assume so. What I'm going to do next is pull the plus 4 out, just like we could. That k, here's your k, plus 4. So that's going to be plus 4 times the integral. We're splitting that in 3 functions. Integral of x from 1 to 3 of x dx. Oh, I left off my dx here. Sorry. Nobody caught me on that? Goodness gracious. Are y'all sleeping at the wheel? Okay. Then I'm going to pull out the minus 3 and do the integral from 1 to 3 of dx. Just dx by itself. Okay? Now, guess what? That's a minus times this integral right here. They told us what its value was. 26/3. Now, they won't always be so nice as to do that, but they did. And then we're going to do plus 4 times this integral right here, and this integral right here, they just told us was 4. So 4 times 4. And then we have a minus 3 times this integral here, and they happen to tell us that integral there was 2. So let's see what we got. Minus 26/3, love my fractions, don't you? Plus 16 minus 6. I'm going to do these two because that's easy. That's going to be 10, and this will be a minus 26/3 plus 10. Well, I'm going to do it this way. Minus 26/3. And how many thirds is 10? That would be 30/3, isn't it? So that's going to come out to be positive 4 thirds. That's what I get. Let's see what they get. Okay. Well, they wrote it out pretty similar to what I did. Okay. They did an extra step here. They did the integral of minus x squared plus the integral of 4x plus the integral of minus 3. They put in an extra step there. I didn't. Okay. And then they pulled out the minus sign. I did that at one fell swoop. Minus the integral of x squared plus 4 times the integral of x minus 3 times the integral of dx. Okay. Now they've got exactly these three functions that we have up here. So that'll be minus 26 thirds plus 4 times 4, exactly what we got, minus 3 times 2, exactly what we got, and they come up with 4 thirds without showing you how, but they got it. Does that make sense? Any questions on that? Now, one more little theorem here. They're not going to give us an example with it, but just a theorem. If y'all don't have any questions, please speak up if you have questions. Okay? If f and g are continuous on this closed interval from a to b, f and g are continuous. Now remember, if they're continuous, they're also integrable. Okay. Now, here's the second feature. 0 is always less than or equal to x, f of x. So that means f of x is never negative, because 0 is always less than or equal to f of x. So f is a non-negative thing. But f is also always less than or equal to g of x. Okay? So that means g is going to be on top, pretty much. F's going to be somewhere in the middle, and the x-axis is going to be at the bottom. Okay? Then the following properties are true. First, the area of the region bounded by the graph of f and f and the x-axis, that's between a and b, okay, must be non-negative. Why? Because f was always above 0. Okay, so that has to be true. Integral of f is always going to be non-negative. Okay. Secondly, the area must be less than or equal to the area under G, because f is always less than or equal to G. Now, if f is always equal to G, then they're going to be the same area. But if f is ever less than G and never greater, then the area under f is going to be less than the area under G. So yeah, this shows that. Okay? Now, with those two things in mind, here, those two properties are generalized here. Preservation of inequality. If f is an integrable function and non-negative on the closed interval a to b, then the area under that f has to be greater than or equal to 0. Okay? If f is always non-negative, means it could be 0, but it can't be negative. Always non-negative, then the integral under f is always greater than or equal to 0. Now, if f and g are integrable on the closed interval a to b, and f of x is always less than or equal to g of x, for every x in that interval a to b, then the integral of f of x dx from a to b is less than or equal to the integral of from a to b of g of x dx. If f is always less than g, less than or equal to, then the integrals of f on some interval a to b will always be less than the integral of g. All right, and that's the last theorem in the section. Okay, now they do a little QR code there, which indicates to me there's something at Larson, well, someplace. It may be at your calcview.com, but they do give a QR code there in the book. Okay, that's the last slide in the section 5.3. Homework exercises here would be number 3. It's at Calc Chat and at CalcView. Any of the odds 5 through 9, they're all at Calc Chat. 7's at Calc View. Either 11 or 13, they're both at Calc Chat. Okay. Any of the odds 15 through 25, they're all at Calc Chat. Okay. Any of the odds 27 to 35, they're all at Calc Chat. 29's at Calc View. Any of the odds 37 to 43, they're all at Calc Chat. 41's at Calc View. Any of the odds 45 through, I'd say 45 or 47, they're both at Calc Chat. 49's at Calc Chat. You can think about doing 51. It should be at Calc Chat. Or 51 or 53. They should both be at Calc Chat. Well, let's do it. You could think about doing any of 51 through 55. They should all be at Calc Chat. You can explore doing any of the odds 57 through 63. No, 57 to 59. They're at Calc Chat, 57 or 59. And then you can also explore doing either 61 or 63. They're both at Calc Chat. Then do either of the odds 65 or 67. They're both at Calc Chat. And then true false, any of the odds 69 to 73. They should be at Calc Chat. 75 you could do if you'd like. And 77 is a proof. You can do that if you would like. 79, you could think about doing that if you'd like. 85 is finding a value. 81, finding a value, if you'd like to do that one. You could think about doing 83. It should be at Calc Chat. And then using a Riemann sum, 85, if you choose. You don't have to do those, but if you want to, you can. Any questions from 5.3? Okay. All right. Now I'm going to end the slideshow for 5.3 and discard it, and then also get rid of it, and then screen sharing stopped. I understand that. I'm going to now share 5.4. All right. Now, as soon as I did that, my bar got in the way again. You can't see it, but I can, and it's in the way. So I'm going to move it down out of the way as much as I can. And we'll start the slideshow from current slide. All right. Can all of you see Chapter 5 integration? Yay? 5.4, the fundamental theorem of calculus. Now they say that now, and they'll turn around and say there's a second one, okay? In some books they call them fundamental theorem of calculus part 1 and part 2. This one calls it the fundamental theorem of calculus, and then the second fundamental theorem of calculus. So however you want to name them, there's two of them. Let's do the first one first. What we're going to do is evaluate a definite integral using this fundamental theorem of calculus. And frankly, I'll tell you, you're going to love it because it's so much easier than doing Riemann sums, than doing limits, or anything else like that. You just do it. Okay? Number 2, understand and use the mean value theorem for integrals. It's going to be a pretty reasonable thing, I believe. We'll find the average value of a function over a closed interval. That's going to be related to the mean value theorem. Then we'll understand and use the second fundamental theorem of calculus and understand and use the net change theorem. Okay. Those are our objectives in this section. How are we doing on time? Okay, we go to 11:40, right? Yeah, 10 to 11:40. So keep up with me. I've got to return a phone call. 2 rang downstairs. May not be able to eat lunch today. We'll see. Okay. You have now been introduced to 2 major branches of calculus. Differential calculus you did mostly in Cal 1, Integral calculus we've been doing, may have started a little bit in Cal 1, now we're doing it in Cal 2. At this point, the two problems seem unrelated, but there is a very close connection. The connection was discovered independently both by Isaac Newton and Gottfried Leibniz. Okay, it's stated as the fundamental theorem of calculus. This probably was another big contention. Who discovered it first? We don't know. Of course, the Newtonians think he did. The Leibnizians believe that he probably did. Who knows? Informally, now I don't find this description particularly instructive, but I'll give it to you because it's here in the book. Informally, the theorem states that the differentiation and the definite integration operations are inverse of each other, in the same sense that division and multiplication are inverses of each other. Adding and subtraction is inversing of each other. Raising to a power, taking a root of that power. Those are inverse operations of each other. So, now, to see how Newton and Leibniz might have anticipated this relationship, consider the following approximations shown here. Now again, both of these standing by themselves are absolutely true. Okay? It's just making the connection between the two is not that intuitively obvious to me. But this is how we did derivatives. We first looked at the slope of a secant line when the 2 points were separated by delta y on the vertical and delta x on the horizontal. The slope of that secant line was delta y over delta x, rise over run. That's from algebra, okay? Way back. But what we did was take shorter and shorter delta x's until that delta x approached 0, and then your slope of the tangent line was, they still say delta y over delta x. They've got to change that. Whoa. Okay. This to me should be a dy dx, okay? Which is okay. I mean, they can still call it that, but that just says that is the limit of this goes to that. All right. Now, in definite integration, the area of a rectangle, of course, is dy times dx. Okay? Area is dy times dx. The area under a curve is its dy, and here again you can approximate this by your rectangular sums, whether they're Riemann sums or regular sums, whatever. It's the change of your y's, the summation of those times your change of your x's. Okay? Now, they have to do something. This is not the same delta y as that is, and not really clear that it's the same delta x as that is, but that's the area under a curve. Okay? Now, somehow this is supposed to, okay, I guess what they're saying, because this is a division relationship and this is a multiplication relationship, therefore you would think the derivatives and integrals would be inverses. That's probably what they're talking about, because this is a division, those are multiplications. Just like division is the inverse of multiplication. I guess that's what they're saying. To me, it's a, okay, big deal. Okay, but anyway, let's move on. The slope of the tangent line was defined using the quotient, delta y over delta x, slope of the secant line. Similarly, the area of the region under a curve was used, defining the product, delta y times delta x, of your various rectangles. Then you go back and take limits. So at least in the primitive approximation stage, the operations of differentiation and definite integration appear to have some type of inverse relationship in the same sense that division and multiplication are inverse operations of each other. The fundamental theorem of calculus states that the limit processes, which we use to define the derivative, or the definite integral preserve that inverse relationship. Okay? It's a stretch, but it's true. So here is what we call anti-differentiation. Throughout this chapter, you have been using the integral sign to denote the antiderivative that gives you a family of function, or a definite integral, which is an actual number. Okay? The use of the same symbol here and here, just without limits and with limits, makes it appear they are related. In the early work with calculus, however, it was not known that the two operations were related. The symbol, the integral symbol, was first applied to the definite integral by Leibniz, was derived from the letter S, which meant sum. Leibniz calculated the area as an infinite sum and thus used capital S, which we'll use in the next chapter. Later we'll get to that. So here's theorem 5.9, fundamental theorem of calculus. If a function f is continuous on a closed interval from a to b, and capital F, this is your little f, there's your capital F, is an antiderivative of that little f. Now, I don't know, it seems like a long time ago we were talking about antiderivatives. And then we stopped and started talking about limits. And then we started talking about sums. And now we finally get around to tying them together. The antiderivative of little f on some interval a to b, then here's what you get. The integral from a to b of f of x dx is simply the antiderivative of f, little f, which is capital F, first evaluated at b, and then subtract from that the evaluation at a. That's the fundamental theorem of calculus. We don't have to use limits anymore. We don't have to use geometric shapes anymore. We can just do the antiderivatives, evaluate them using this simple expression. You've got your answer. Okay? So the following guidelines, that covered, by the way, page 317 in the top of 318, here are the guidelines to help you understand the use of the fundamental theorems of calculus. Provided you can find an antiderivative of f. Not all functions are easily discernible and sometimes impossible to find that antiderivative. But if you can, you now have a way to evaluate a definite integral without having to use the limit of a sum. I should hear cheering in the background, do I? No, y'all like your limits, don't you? Okay. Hey, I saw 2 hands go up. Okay, clapping hands. Good deal. Okay, Andy and Brandon still asleep. No, I'm sorry. Okay, never mind. All right, thank you, Ashton and Jordan. There's Brandon, gives me a thumbs up. Okay, Andy's still asleep. Okay, whatever. So let's move on. The following guidelines help you understand that. Provided you can, without using limit. When applying the fundamental theorem of calculus, the notation shown below is convenient. If you do the integral, which you can think of that as antiderivative of f, if you can determine what that is, then evaluate that from a to b. A on the bottom, b on top, just like it was here. And that means take your capital F, evaluate it at b, subtract from that capital F, evaluated at a, you're done. For instance, to evaluate this formula, this integral from 1 to 3 of x cubed dx, you can write, and let me go on and write it here. They've already got it written down. But just to remind, it's been so long since we've done this. This will be when you're doing the antiderivative of x cubed. What we do is increase that exponent by 1, make it x fourth, and divide by that new exponent. That's x fourth over 4. Did y'all remember how to do that? And then you evaluate that from 1 to 3. And what does that mean? we evaluate 3 to the 4th power over 4 minus 1 to the 4th power over 4. Evaluate it first at 3, then at 1. Well, this will be 81 fourths. 3 squared is 9, 9 squared is 81. So that'd be 81 fourths. I said fourths and wrote a 1. Don't know where the disconnect is, but there's a fourth down here somewhere. Okay? Minus 1/4, because 1's fourth to the 4th is 4th. This is 80 fourths, and that is 20. There you've done an antiderivative and definite integral using the fundamental theorem of calculus, and guess what? We did not have to use one of those I formulas. Remember that I to the 3rd? Ooh, that was messy. But guess what? We don't have to do that anymore. There we have it. It's equal to 20. It is not necessary. Okay, now I'm going to show you a couple of other things too. As soon as you did this, you could have pulled that 1/4 outside and just done 3 to the 4th minus 1 to the 4th. That would be 81 minus 1. It's 80. Then divide by 4. It doesn't matter. It is not necessary to include a constant of integration c in the antiderivative because it's a definite integral. If you don't have the limits here, the b and the a, you have to do a plus c. But you see, if you put it in, here you do f of x plus c minus evaluated b, then evaluated a, that would be f of b plus c minus f of a plus c. Well, this plus c and this minus c add to 0, and you just have f of b minus f of a. So you do not, if you're doing definite integrals, do not need to worry with plus c's anymore. If they're indefinite integrals, just antiderivatives, absolutely, you have to remember your c. Okay. Make sense? All right. So let's do some. Evaluate these definite integrals. All right. How are we doing on time? Oh, we got 9 minutes. Let's do as many as we can. All right. Now what we're going to do, antiderivative of x squared. Someone tell me what that is.
Antiderivative of what?
X squared. X cubed over 3 minus, what's the antiderivative of 3? 3x. Perfect. We're going to evaluate that from 1 to 2. Okay? Meaning we're going to plug in the 2 first. That will be 2 cubed over 3 minus 3 times 2. Can I go and write down 6? Minus. Now watch these minus signs, folks. They're there to trip you up. That's the only purpose for a minus sign, is to trip you up, right? You're subtracting the other one. Now, if you want to, put parentheses around it, if that's helpful to you. We don't have much time, so I'm going to try to do it without it, but you'll find out I get tripped up sometimes. That'll be 1 cubed divided by 3. 1 cubed is 1. Then minus a minus gives you a plus. 3 times 1 is 3. Okay, so what does this give you? 8 cubes, 8 thirds, I can't talk, minus 6, minus 1/3, plus 3. Well, 8 thirds minus 1/3 is 7 thirds, minus 3, minus 6 plus 3 is minus 3, and that would be 7 thirds minus 9 thirds, because 3 is 9 thirds. That should be negative 2 thirds. Let's see how the book did. Yes, they got it right. Okay. How about this one? Okay, now, any questions on that? I know I did it sort of fast because we're running out of time. Any questions? Yeah. Okay. Did you follow, or did I skip too many steps?
Oh, no,
Okay, now this one, I never like to try to integrate a radical or a variable in the denominator if I can help it. Okay, so what I'm going to do is rewrite this as an exponent, not as a radical. So this will be the integral from 1 to 4 of 3 times x to the what power? 1/2 power dx. Now, I'm going to use one of my principles before. Let's take that 3 on the outside. I don't like it in there. Okay. Now, let's just evaluate the integral of x squared, x to the 1/2. That would be x to the 3/2, right? You increase that by 1, and then you divide by the new exponent, which is the same as multiplying by 2/3, right? Yay or nay? Been a long time since we did those. Okay, plug this in from 1 to 4. Okay, now before I do anything else, I'll notice this 3 and that 3 divide away. So let's do 2. I'm going to pull the 2 on the outside too. No reason messing with that. Now, when you have a fractional exponent, most of the time I like to go on and use the denominator first. That means take a square root of 4. Square root of 4 is 2, and 2 cubed is 8. Agreed? And then we'll take the square root of 1, which is 1, and 1 cubed is 1. So this will be 2 times 7, which should be 14. Let's see how they did in the book. Good for them, they got that one right too. Okay. Uh-oh, SpaghettiOs. All right. Here we have this one. Does anyone recall what the antiderivative of secant squared is? Tangent x. Remember, the derivative of tangent is secant squared, so the antiderivative of secant squared is tangent. Go back and review your trig derivatives and antiderivatives. Okay, and that tangent x is evaluated from 0 to pi fourths. So this is going to be the tangent, and you just plug in this as the x, tangent of pi fourths minus the tangent of 0. Anyone remember what the tangent of pi fourths is? How many digits? 1. Okay, that's what it was. So this is equal to 1. That's not supposed to be a theta, that's supposed to be a 0. What's the tangent of 0? 0. So that's 1. Let's see how the book did on. Oh my goodness, they got that one right too. Okay, how much time we got? 2 minutes. Let's just watch how they did theirs. Oh, here's the new page. Okay, the antiderivative of x squared is x cubed over 3, just like you said. Antiderivative of minus 3 is minus 3x, just like you said. We evaluate that from the upper limit, from the lower limit of 1 to the upper limit of 2, which means we plug in the 2 first. 2 cubed is 8 over 3 minus 6, and then we subtract from that, and they put the parentheses. They aren't in a rush like I was. And plug in the 1 cubed over 3 minus here 3 times 1, and then the minus sign here changes both of those signs, so that'd be 8/3 minus 1/3, which is 7/3, minus 6 plus 3 would be a minus 3, and they just amazingly got that to be negative 2/3, which is what we got to. We worked it out they didn't. 7/3 minus 9/3 is negative 2/3. Second one, they did do it this way. They pulled out the 3, good for them. Wrote the x squared as x to the 1/2, good for them. And then did your antiderivative of x to the 1/2 is x to the 3/2 over 3/2 or times 2/3. So that would be 3 times x, and they wrote it weirdly, x to the 3/2 over 3/2, evaluated from 1 to 4. Much easier to deal with. They just threw the answer here. Would have been easier to deal with if they had written this as 2/3. Then the 3's cancel out, and your 2 would have been on top. 2 times the square, let's see, 4 to the 2/3 minus 2 times 1 to the 2/3. Okay? The square root of 4 is 2. 2 cubed is 8. So 2 times 8 would be 16 minus 2. Okay? Which would be 14. Because the square root of 1 is 1. 1 cubed is 1. So that's just minus 2. 14. Good for them. And the next one, the antiderivative of secant squared is tangent. Evaluate that from 0 to pi/4. That'd be the, they don't write it down. They just say that's 1 and that's 0. 1 minus 0 is indeed 1. Good for them. Okay. Any questions on those? Okay. We will start next time not at mean value theorem. We will start at, somewhere I have a pencil, example 2. They're skipping example 2, 3. Yeah, they're skipping 2 and 3. We'll pick up with example 2. Any questions on anything we've done so far in 5.4? Okay. Now, all right, homework exercises here on page 328. You can do either 5 or 7. They're both at calcchat.com. And then I think you can do any of the odds 9 through 33. Okay, they should be at calcchat.com. Number 17 is at calcview.com. I think you can probably also do, let me just see. No, we'll wait and do the rest of those next time. Okay? Any questions? Good deal. What's that again? Yeah, I got all of you here. Remember, I was screaming and yelling about perfect attendance. It may have been before your sound was connected, but that's why you didn't hear me. So as soon as I saw you come in, I had you marked. But it's good for you to ask. Keeps me checking to make sure I got it right. All right, good deal. Any other questions? All right. Now, okay, let's move on. Any other questions? I'm going to stop sharing. I'm tired of sharing, sick and tired of sharing. Okay. And we've gone 2 minutes over, but guess what? There'll be no extra charge today. Do you have anything else before I end the meeting? Speak now or forever hold your peace. Okay, take care. Yeah, was that a question? Okay, all right. Then we'll see you on Wednesday morning, okay? Take care. All right. We'll see you Wednesday.